Welcome to my YouTube channel. Today I'll be discussing the addition of wireless to the security circuit presented in previous videos with schematic details and 3 demo presentations. Since I have some extra printed circuit boards with the same layout as shown on this security system board, which will be briefly demoed somewhere in the middle of this video, I am giving away 5 do-it-yourself security system circuit boards with free shipping to the first 5 subscribers who send an email that includes a United States physical address in the email to my email address listed in the description below this video. If you later decide to use this board for personal use, you will need to purchase the components for the printed circuit board and solder the components, which will require a soldering iron between 650 and 750 Fahrenheit, depending upon the thickness of the terminal you are soldering with 60-40 flux core, while each solder should take less than 5 seconds to complete, or you risk burning up a chip. If you are experienced in electronics, you can order the components from a third-party electronics supplier, since there are enough references on the top silk of the PCB. At the same time, to ensure you get the correct components, I will consider supplying the components for a fee. In this security system panel, the Honeywell auxiliary power supply board is manufactured with only 2 mounting holes. And since this is only a 2-layer board, and I can see the pertinent circuitry, I carefully drilled 2 additional holes in the auxiliary power supply board for greater mounting stability. While the panel was repurposed from a security circuit design more than 25 years ago, any discoloration of the panel was due to excessive heat from the old circuit board. At the bottom of the panel, there are multiple external motion sensors wired in series, and 4 manual switches for the 12-volt supply to the security system, 12-volt supply to the motion detectors, siren horn bypass, and sensor bypass. Since not all switches are on or off at the same time, these switches can form a 4-pin combination. If you use 4 identical switches without external labeling and lock the cabinet door, if someone throws an unknown switch, the alarm could activate for several minutes. If at any later time, and for if and when needed, if you rearrange the switches, such as changing plugs in the back of the switches, it will be like changing a 4-pin combination. For detailed information on the security circuit with battery backup, see my security circuit with auto reset video. Regarding a wireless enhancement to the security system, I initially thought about designing my own 433 MHz wireless circuit while soldering the receiver components on the security board and the transmitter components on the external device boards. After researching auxiliary transmitter and receiver boards from third parties, I discovered they only cost a few dollars, although this open source type requires additional encoder and decoder chips. After further research, the following 433 MHz transmitter and receiver costs less than $10, and not only includes the encoder and decoder, it has 4 channels while supporting third-party generic devices that transmit 433 MHz and use a 1527 learning code. While the 433 MHz range is advertised up to 160 feet or more within a line of sight, I have thoroughly tested these boards without a line of sight, using the supplied antennas when placing the transmitter in an enclosed outbuilding 100 feet away from the receiver that was placed in an enclosed main building. If the range needs to be extended, rather than trying different antennas with different wavelengths of which could damage a chip, first uncoil the antenna and test, and then if you need more range, a repeater can be added. This type of readily available transmitter repeater can be used on 433 MHz transmissions and can handle both manually fixed codes and automatic learning codes. The following are readily available devices supporting the 433 MHz frequency and 1527 learning code. Wireless remote control, which can also be used as a panic button to activate the alarm. Wireless door and window sensor, which will be tested near the end of this video. Wireless motion detector. To find other supporting devices, an internet search for 433 MHz 1527 wireless should return more supporting devices. The advantage of using photoelectric sensors is rather than a motion detector, you can be near the sensor without activating the alarm. In addition, Rather than a moving door sensor, the door can stay open while the alarm can stay on. At the same time, even if you are not near an open door protected with the photoelectric sensor, if someone breaks the sensor beam by walking through the door, the alarm will activate. This type sensor can be especially useful for porches, patios, garages, and sheds. In a previous video, I mentioned how a buck converter can interfere with radio frequencies. However, since the 2576 buck converter chip I am using is rated at 52 kHz, the only external frequencies that might be susceptible to interference are in the kilohertz range, such as AM radio in close proximity. To add wireless megahertz support for the photoelectric Genie sensors, and while the Genie sensors will still need wiring between the sensors, the Genie board and security board connection will be wireless, as will be demoed with breadboard prototypes later in this video. In the following Genie board RF schematic, which is mostly the same as the Genie board schematic detailed in a previous video, and therefore I will only discuss the additions, the first addition is using a 6-pin header for more header strength, rather than using 2 smaller headers. Pins 1 and 2 are still for line and ground, and pins 3 and 4 are optional for hard wiring into the security circuit. Pins 5 and 6 are for the Genie sensors. Another addition is using the other comparator inside the LM358 IC chip. The reason the other comparator is needed is because comparator A is normally high, while comparator B is normally low. To achieve this effect, the plus and minus wiring is reversed. After the Genie sensor beam is broken, and the sensor voltage on pins 5 and 6 becomes higher than 10 volts, comparator B activates an NPN transistor to pull down the transmitter circuit. The external third-party transmitter has 7 pins plugged into an 8-pin header, while the 8th pin is for the antenna. The 4 dip switches allow changing channels. At the same time, only a single switch should be on at a time, while a correlating dip switch on the security system must also be on. The correlation is not corresponding with the numbering on the components, since the numbering is inversed with the transmitter and receiver I am using. If the transmitter ever fails in the future, the transmitter, like the receiver in the following security system RF schematic, can be replaced by simply unscrewing the terminals on the header. In the following security circuit RF schematic, which is mostly the same as in my security circuit with auto reset video, with some enhancements detailed in my photoelectric garage door safety sensors video, I will comment only on the RF additions. Like the RF transmitter, the RF receiver for this circuit also has 7 pins, although, unlike the transmitter, the receiver only requires a 7-pin header, since the antenna is soldered on the receiver board. Like the Genie RF board, there are also 4 dip switches for the 4 different channels. Although, unlike the Genie RF board, one or every dip switch on the security RF board can be turned on. The RF logic addition is adding inverter 4 with an NPN transistor to pull down the normally closed external sensor circuit to activate the alarm. If using only RF with no hardwired external sensors, then a jumper should be placed between pins 4 and 5 of the 5-pin header. Regarding the second of 3 demos, as in my previous video, I will preface this demo by stating the sequence of events and key observations. First, observe the Genie sensors, where I will manually block the sensor beam. Second, the red lights on the transmitter and receiver will turn on, while the frequency on this type of 2-way radio frequency counter will at least display a high VHF megahertz frequency. Third, the blue and red lights on the security board will turn on, representing the alarm. After unblocking the Genie sensors, and while the alarm is still activated for a calculated period of time, the lights on the transmitter and receiver will turn off, while the frequency will gradually decrease on the frequency counter. After a brief delay, the blue and red lights on the security board will turn off, representing the security system auto resetting. Regarding the third-party door and window sensor demo stated earlier in this video, I will also preface this final demo. First, I will manually separate the sensor. Second, a red light on the receiver will briefly turn on, while a frequency will register on the frequency counter. Third, the blue and red light on the security breadboard will turn on, representing the alarm. While the receiver can handle multiple transmitters, before this demo I pushed a button on the receiver once to activate the 1527 learning code, and then separated the sensor to transmit for the receiver to learn this sensor. As in the previous demo, after a brief delay, the blue and red lights on the security board will turn off, representing the security system auto resetting. If you like this video, or just learned something in this video, please click like on the YouTube page below this video.